Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mukhriz bin Mazlan. I'm here to present on my progress report. I'm currently a third semester master student. I'm currently under Dr. Riza Effendi of FTTC Lab. The title of my research is the flight stability augmentation of an agricultural UAV via software in a loop flight simulation. What that means is that I am researching on the flight stability augmentation that will be implemented into the agriculture UAV that I will present later via a software in loop flight simulation. The contents of my videos are as follows. To introduce you to the field of using UAVs in agriculture, within the field of agriculture, over vast areas of crops requires the use of machinery and tools to help cultivate. Malaysia's fields require the use of trucks, farm vehicles, as well as four-wheeled motorcycles to be able to manage their crops properly. UAVs can be the solution to cover large fields of arable land with whatever the crop needs, be it insecticide, pesticide, water, or even the seeds themselves. Introducing a design from Dr. Riza Effendi, a fixed-wing multi-rotor hybrid that is capable of extending flight time of what a typical multi-rotor UAV can do. It's very different from any other design because it has no control surfaces like you would see on an airplane. It has also been estimated to be able to carry a 5 kilogram load. It has a 10-foot wingspan, which makes it quite big enough to carry that 5 kilogram load, and with the correct augmentation, it is able to fly perfectly. For context of the project, we wanted to create an easy to fly UAV for farmers, which for the means of spraying insecticide, pesticide over their land and being able to for them to fly it themselves. That in turn will reduce the cost of purchasing and conducting the UAV, as well as improving on the old methods of taking care of crops. My objectives are as follows: to investigate the flying quality and the dynamic stability of fixed wing multi-rotor hybrid means that I will be investigating on its flying quality based on its geometry and as well as its dynamic stability based on the flight simulations. To synthesize a suitable control method augmentation where from the previous objective I'll be able to synthesize it, a control method that will be implemented that could make it much more stable, and finally to evaluate that to get its final flying quality control method. The segments of my research are as follows. To introduce you to my methodology and data collection, I will introduce you to a software that I have been using to create the plane that you see now today. It is called Explain 11 and I will show you shortly how it works. This is Explain 11's menu. Explain 11 as a background context, Explain 11 is a flight simulator software that is available in Steam, available for download, and it is a flight simulator that has been used to train pilots before they fly the real thing. It is also perfect for us engineers to design our own aircraft or UAVs and test them out in a sort of simulated world without the dangers of having an actual UAV take off. So this is what the design looks like in the simulator. I've labeled each of the rotors accordingly. You will see why in a moment. But essentially, the rotors are fixed that way because this is how Dr. Riza Effendi wanted it to be. So I will treat you to a short video of which I will show you how the UAV actually behaves in the flight simulation. So this is the menu that you will go into when you need to go for a let's say a flight during this using this software. I'll quickly show you a little bit, but this is what you would see when you wanted to get a data output of what we're going to discuss later on. But essentially, when you have created an aircraft in Explain 11, you're able to fly it, and then you can set what kind of parameters of data that you want to see after the flight. So this is me showing you a little bit on how you want to get that data out of there. So you go to the flight configuration, data output, and then you kind of select which kind of data that you want to see in a graphical in Excel, so that you can essentially just craft your own what do you call this, augmentation through there. Let's speed it up to the point where I'm taking off. Right. So when you start off on your airplane in X-Plane 11, you'll see that you're in the cockpit as a normal setting. So here I'm going to show you a little bit on what it looks like on the runway. As you can see, it's fairly small, but just a reminder that this is a runway. This is supposed to be for like Airbus and giant airplanes. So this is what it looks like up close. So as you can see, everything in the simulation works perfectly, and you can see that I've started the engines on the craft. So to fly this plane is a lot similar to how you would fly a multi-rotor drone, just a lit with additional parameters such as lift and drag dialed up to 11. Yep. So this is what is called a rolling takeoff. You can see this sometimes if you go into YouTube and you see the Harrier jets. They will take off from the runway at a rolling fashion, very slowly going into getting up to speed. Excuse the a bit of tangent there, but essentially when you take off, it takes off directly up once you have built up a little bit of speed there. So here in the flight, I can show you that the plane itself doesn't really what do you call this, behave like a multi-rotor drone, even though it essentially is a multi-rotor drone with added wings. But essentially, with the added wings and the tail and the secondary wing at the back, you essentially get all the benefits of a fixed wing aircraft using multi-rotor components. So again, I must reiterate that we have no control surfaces here. That means we have no flaps, we have no elevators, and we have no ailerons. So that means everything is being controlled using the four rotors. I'm going to show you a little bit on how I demonstrate its ability to not reduce its altitude, even though we're using a maneuver that is commonly used for airplanes. Here you are. So as you can see, I'm starting to try to get this UAV to a lower altitude, but it is very, very difficult for it to kind of like negate that. It's because of its own structure and its own the way it's already designed. It's very, very hard for it to go down. So you might ask yourself, well, how would I want to go down? So I'll show you in a little bit. So right at the end here, so you'll see how I kind of like land this UAV. So you kind of have to turn off the engines a little bit, but that is just to induce the auto gyro kind of like capability there. So essentially, when you think about aircrafts with propellers, right, when you don't have any power, they will still have a little bit of lift because the rotors on the fans actually help it to keep it up. But this is how I actually landed. As you can see, I turned off the engines, but I'm still using a little bit of that power to kind of control it left and right. This is me trying to get it to align with the runway. But essentially, you can see how smooth it actually glides down, even though it has what we say a non aerodynamically inclined body. So this is touchdown, just a little bit to the left, and landed. Right. So as you can see from the flight simulation itself, it behaves very similarly to what a normal multi-rotor UAV would behave like, with the added bonus of having a fixed-wing aircraft body. Yeah. So once, like I showed you just now, once the data outputs are selected and you've flown the aircraft itself, it is going to be extrapolated onto an Excel sheet, like the one you can see on the second image there. So you can graph all this data into Excel, obviously, and then you can see how much it kind of behaves. So this is my status milestone. I'll be discussing the data that this is from the flight just now. So this is the velocity versus time. Essentially, I'm showing you how it reaches to a certain velocity and it peaks around 21.16 meters per second. That's pretty fast for a UAV. And it shows you that the flight took around like 8 minutes. And generally, you can graph any kind of flight parameter, and then you can essentially see how you would edit or kind of like modify the control to your needs and make it much more stable. So you can see the second graph is about altitude. So I reached an altitude of 290 feet at the, let's say, 5.5 minute mark, right? So it's a pretty high altitude that is in a simulation, right? So this is kind of like the positions of it. So you can kind of see that I'm doing kind of like a turn around and just going back to the runway again. But this is the graph that I could get from the data extrapolated as well. All right, so this is what the nitty gritty of trying to edit the control augmentation to a certain point where you can make it so stable, right? So this is the rudder stick versus the true heading. What that means is the stick that I'm using to control the aircraft, the rudder function is what is supposed to be when you want to kind of like move your yaw angle, right? You want to get it to a certain point where it's either stable or you want to turn it to the left, you go left, turn the right, right? So it responded accordingly to what my commands are. As you can see from the right side of the graph, that is my command from 0 to 1.5 to and negative 1.5. That means it's left and then right. All right. So and the darker green color is the true heading. That means the center axis of the UAV is either facing that way or that way in a 360-degree circle, right? So if it's 150 degrees, that means it's going this way, 150 degrees clockwise, yeah, and 150 degrees, and if it's not going that way, it's going that way, right? So going on, this is the aileron stick and roll degree. And again, I must reiterate that we have no control surfaces. So the aileron stick is completely controlling the four motors on the graph. So that means if I turn left and right, that means the number 2 and number 3 motors are going this way, having a higher power than the ones on the 1 and 4, right? So later on I'll show you a little bit more detail, but essentially this is showing you the response of the stick towards the roll degree, which is kind of like how it kind of moves from the axis in the x-axis, right? This is the elevator stick versus the pitch. So that means the elevator stick, I'm trying to move it up and down. Again, no control surfaces, there's no elevators or control surfaces, it's just controlling the motors. So this is the kind of response that you kind of get. It kind of go when you want to control it up, it actually follows it, but not to a certain degree. It's like it's not exactly like an airplane, but it's not exactly like a multi-rotor UAV as well, right? So this is what the thrust looks like over time, over the course of the flight. This is the same flight, right? You can clearly see that each of the rotors are behaving according to which side they are on, right? So you can see thrust 1, thrust 2, 1 and 2 are this and this, left and right. It's not one row together. So if we think about it, it's 2 and 3, and then 1 and 4, left and right. So let's say 1 and 4 are left, 2 and 3 are right. And this is what it looks like when it compares to the elevator stick response. So this is what I'm trying to show, is that the elevator stick, when I'm trying to give it a command, and this is what the throttle of each of the rotors look like, right? So I'll go into a bit more detail in my dissertation, but this is just a snippet of what you can get from the graph, and you can actually zoom in into the time frame and see the kind of behavioral nodes that we can essentially edit into the control augmentation. This is the aileron stick. This is me trying to kind of like go left and right. uh, and this is the rudder stick going up and down, trying to kind of like fix it to a certain point where it kind of like goes stable. Oh, that's about it. Okay. So this is my Gantt chart. Here's I'm going to show you a little bit that uh, I am on course with finishing my research. Currently, I just finished trying to make these flight simulation work, as well as extrapolating the data for me to discuss on. And on schedule, I'll be doing the real flight test, as in I will be conducting I will be making a proof of concept uh, uh, drone, and I will try to fly it and see its ability to fly compared to the simulation. So, what is the status of my publication? I'm planning to publish in SARES. SARES is an international sustained aviation. It's mainly from Turkey, and it is highly recommended in the aviation community. The status of my thesis writing, currently the data from the flights can be extrapolated. Other parts such as the proof of concept and the wind tunnel test will be conducted in parallel with me writing the thesis. So my planning for next semester, as I mentioned, is a proof of concept flyable prototype and the publication of my research in Aerospace Journal, where inshallah, if I'm able to complete it, I'll be awarded for masters. So this is what my design looks like in AutoCAD. It can be exported into AutoCAD, and on the bottom left there is my simulated 3D printing, where I'm already planning on 3D printing this design onto a onto the what do you call this onto a 3D test bed, and then assemble it essentially, because not only do I want to highlight that I am editing it in AutoCAD because I want to add like holes for the what do you call this for the spines, holders for the rotors as well. That one can't be seen in Explain, but it should be seen in AutoCAD when you 3D print it, of course. And that's about it. Thank you so much for your time, and I hope this reached you well. Bye.